the universe can be a violent place. Collisions scar the surfaces of planets, black holes capture everything in their path, and massive explosions catapult matter far out into space. But how exactly do processes like these unfold? To find out, researchers are using the SLAC National Accelerator Laboratory to recreate the extreme universe. SLAC National Accelerator Laboratory was established in California in 1962 with the goal of accelerating electrons to nearly the speed of light to help study subatomic particles. We now have high-power lasers to create extreme states of matter, cutting-edge X-ray sources to analyze these states at the atomic level, said SLAC scientist Siegfried Glenzer. 3 recent studies have shown just how lab experiments can reveal more about meteor impacts, the cores of giant planets, and cosmic particle accelerators. The first study aims to find out if meteor impacts on graphite can transform it into diamonds. Scientists have predicted these impacts might be powerful enough to produce a form of diamond, called lunstallite, that is even harder than regular diamond. The existence of lunstallite has been disputed, but we've now found compelling evidence for it, says Glenzer, the co-principal investigator of a study published March 14 in Nature Communications. The team heated the surface of graphite with a powerful optical laser pulse that set off a shock wave inside the sample and rapidly compressed it. By shining bright, ultra-fast X-rays through the sample, the researchers were able to see how the shock changed the graphite's atomic structure. A second study, published today in Nature Communications, looked at another peculiar transformation that might occur inside giant gas planets like Jupiter. At high pressure and temperature, liquid hydrogen is believed to switch from its normal, electrically insulating state into a metallic, conducting one. Understanding this process provides new details about planet formation and the evolution of the solar system, says Glenzer, who is also the co-principal investigator of this study. Although the transition had already been predicted in the 1930s, we've never had a direct window into the atomic processes. That is, not until Glenzer and his fellow scientists performed an experiment at Lawrence Livermore National Laboratory. The facility allowed them use the high-powered Janus laser to rapidly compress and heat a sample of liquid deuterium, a heavy form of hydrogen. They then created a burst of X-rays that probed subsequent structural changes in the sample. The team saw that above a pressure of 250,000 atmospheres and the temperature of 7,000 degrees Fahrenheit, deuterium indeed changed from a neutral, insulating fluid to an ionized, metallic one. Computer simulations suggest that the transition coincides with the separation of the two atoms normally bound together in deuterium molecules, said lead author Paul Davis, who was a graduate student at the University of California, Berkeley and LLNL at the time of the study. It appears that as the pressure and temperature of the laser-induced shock wave rip the molecules apart, their electrons become unbound and are able to conduct electricity. In a third example of the extreme universe, tremendously powerful cosmic particle accelerators, near supermassive black holes, for instance, propel plasma hundreds of thousands of light-years into space. The energy stored in these streams and in their electromagnetic fields can convert into a few extremely energetic particles, which produce very brief but intense bursts of gamma rays. Scientists want to know how these energy boosters work because it would help them better understand the universe. It could also give them fresh ideas for building better accelerators, particle racetracks that are at the heart of a large number of fundamental physics experiments and medical devices. Researchers believe one of the main driving forces behind cosmic accelerators could be magnetic reconnection. This is a process in which the magnetic field lines in plasmas break and reconnect in a different way, releasing magnetic energy. Researchers ran a number of computer simulations that predicted how plasma particles would behave in such experiments. Our results are a recipe for the design of future experiments that want to study how particles gain energy through magnetic reconnection, said study's lead author, Samuel Tatorka. The experiments will be discussed at the 11th International Conference on High Energy Density Laboratory Astrophysics, to be held May 16 to 20 at SLAC.